Hello, so this is a revision video for APChemistry 2.3, Structure of Ionic Solids. This is a revision video, which means we just go through the essential information you need to know. For deeper explanations and for full lessons, please check the links in the description below. Ionic compounds generally have high melting and boiling points, meaning they exist as solid lattices. Highly ordered structures which contain positively and negatively charged ions arranged in a repeating regular pattern. This structure arises from strong electrostatic forces between the oppositely charged particles. In an ionic solid, cations and anions, so positively charged and negatively charged ions, are arranged in a regular three-dimensional grid. The reason for this is because for the solid to be as stable as possible, it needs to maximize attractive forces between opposite charges, so cation to anion, and minimize repulsive forces between like charges, so cation to cation and anion to anion. Each ion is surrounded by multiple oppositely charged ions, helping maximize attraction throughout the solid crystal. You don't need to know the specific different types of crystal structure or unit cells, but you should be aware that oppositely charged ions will always arrange themselves to maximize attraction and minimize repulsion. We can explain the stability of an ionic lattice using Coulomb's law, where the force of attraction between the ions is proportional to their magnitude of charge, so the charges they have, and the distance between the center of each ion. This helps mathematically explain why the oppositely charged ions will be as close to each other as possible, because then the r² part of the Coulomb's law equation will be as small as possible, meaning the force will be as big as possible. The stronger the force of attraction, the more stable the ionic lattice, and the higher the melting point of the ionic compound. The structure of an ionic lattice also helps explain many of the macroscopic properties that ionic solids have. For example, as we've already said, the high melting and boiling points due to strong electrostatic forces of attraction, but also their brittleness. If you hit an ionic solid, you force the layers to shift, and then like charges can get close to each other, and this causes repulsion, forcing the crystal to break apart. Effectively, you force the same charged particles to get close to each other and further away from oppositely charged particles. Electrical conductivity of ionic compounds can also be explained using ionic lattice modeling. In solid state, ionic compounds can't conduct electricity. This is because the charged ions are fixed in place and can't move freely and carry charge. However, if you melt an ionic crystal or dissolve it in water, then now the charged ions are free to move. This means charge can flow through the substance, enabling the conduction of electricity. Remember, for electrical conductivity, charged particles have to be able to move freely. This is also the same for in metallic structures where delocalized electrons are able to move. We often represent the arrangement of ions in a lattice using particulate model diagrams. Here we show the positive and negatively charged ions alternating in a regular 3D arrangement. The ions are shown as perfect spheres, and the sizes are usually approximate to the ionic radius of each ion. However, they are normally drawn with spaces between the ions. This isn't actually true of how the ions are arranged in an actual ionic solid. However, it can get quite complicated to show this, so we normally draw ionic lattices as unit cells, with ions being placed in corners of a cube to represent how the ions are arranged. But please do remember that in reality, oppositely charged ions are touching and are packed as tightly together as possible.